7.5. Write and graph exponential decay functions. For this lesson, we're still going to continue to explore the concept of exponential functions. In 7.4, we learned about the exponential growth model, which is a type of exponential function where the graph curves upward from left to right. But for this lesson, we're going to learn about the decay function, which is another type of exponential function in which the graph curves downwards from left to right. Okay, so we can still model this by y equals a times b to the x power. A, again, does not equal to 0. B is between 0 and 1, not inclusive, and b does not equal to 1. So if I give you a simple example here, y equals half to the x power, where a equals to 1, meaning the coefficient in the front, then the graph of this exponential function, or specifically decay function, is represented by this graph here. As you can see, when we plug in the points 0, y equals 1. We plug in the points 1 for x, y equals to half. And when we plug in 2, y equals to 1/4. So if we keep plotting all these points, we would get a curve that curves downwards from left to right. Okay, so to describe this graph, we can say it is a smooth curve through the points. And if a equals to 1, then the y-intercept is always 0, 1, with the graph curving downwards from left to right. And the domain will be all real numbers, and the range will be y greater than 0 or all positive real numbers. Okay, let's look at a different graph here, where a is greater than 1. So I kept the original graph, y equals half x, okay, so that we can compare it to the new graph. So when I graph the new graph, there's a difference. When I plot 0, or substitute 0 in for x, y is 3. So I notice that there's a shift upwards along the y-axis. And if I plug in another point, such as 1, then y is 1.5. So 1, 1.5. And as long as there's 2 points, we can draw the graph. And to describe this graph, we can say it's a vertical stretch of the graph of y equals half to the x power. And if a is greater than 1, meaning this number here, then the graph shifts up the y-axis for this graph to the y-intercept 0, 3. This point. And 3, to describe the domain, we will say it's all real numbers, and the range will be all positive real numbers, or you can simply write y greater than 0. Now let's look at this graph. Here a is negative. So I'm using 3, negative 3, to make it simple. I'm going to plot 2 points. I'm going to use 0 because it's the easiest. Half to the 0 power is 1. 1 times negative 3 is negative 3, so the y-coordinate will be negative 3. That's, I'm going to plot that. 1, 2, 3. I'm going to label the point. And then I'm going to use 1. So half to the first power is still half times negative 3 is negative 1.5. So I'm going to plot that as well. Okay, as long as I have 2 points, I can go ahead and draw the graph. So this is 1, negative 1.5. As you can see, this graph is a reflection of this graph. Okay, so if I were to move this graph over 1, 2, 3, 1, 1.5, you can see it better. Okay, and what do we notice here? Number 1, y equals negative 3 times half to the x power is a vertical stretch with a reflection in the x-axis of the graph of y equals half to the x power. And we can also say that when a is less than 0, or when it's negative, then the graph shifts down the y-axis. For this graph, to the y-intercept, 0, negative 3. And for the domain, it will be all real numbers, and the range will be all negative real numbers. Or you can simply write y less than 0. Okay, let's take a look at this exponential decay function. Y equals half times half to the x power. In this case, a is between 0 and 1, meaning it's fractional. And let's see what happens to the graph. I'm going to first graph y equals half to the x power. So 0, 1, and 1 half. So here we have 0, 1, and 1 half. And we can connect the dots. Okay, now I'm going to graph this exponential decay function. When I substitute in for 0, half times 0 is 1 times half. And then I'm going to use the point negative 2. Okay, and half to the negative 2 power, okay, will give you 4. And 4 divided by 2 is 2. So let me work that out to show you what I just did. Okay, so we can go ahead and plot these points. 0, half, and negative 2, 2. So I'm going to go ahead and connect the dots. And just to keep in mind that these exponential functions never go to 0. Okay, they just get smaller and smaller. And when we describe this graph, we can say it's a vertical shrink of the graph of y equals half x, or half to the x power. Okay, as I showed you here, this is y equals half to the x power, and this graph here is y equals half times half to the x power. So the coefficient here, the a, tells you that it's a vertical shrink. And again, the domain would be all real numbers, all the x coordinates, and range will be everything above the x-axis, or we can just say y greater than 0. Okay, all your y coordinates above 0. And for this next graph, I would like to first graph y equals half x again. So 0, 1, and 1/2. I'll connect my dots. Okay, and then y equals negative half times half to the x power. I'm going to use 0 again. Half to the 0 power is 1 times negative half is half. And then I'm going to use negative 2. Okay, I'm going to work it out here. Half times negative 2 is 4. And I'm going to multiply this to negative half. I'm just trying to substitute negative 2 in for x here and solve for y. So this would be negative 2. So now we have 2 points. So 0, negative half. Let me use a different color. And then negative 2, which is here. As you can see, after you plot these points and draw the graph of y equals negative half times half to the x power is a reflection in the x-axis of the graph of y equals half to the x power. So this, we can also say that this graph here is a vertical shrink of y equals half to the x power. Okay, as you can see that this graph is curving outwards more compared to the blue graph. Okay, and the domain is again still all real numbers, and the range will be y less than 0 because now the graph is below the x-axis and we want all the y coordinates that are less than 0. Okay, now let's take a look at some problems involving exponential decay functions. Okay, in part A, guided practice, it asks you to write a rule for the function. So if we look at the chart here to the right, we can find out a pattern. I notice that I can add 1 between the x coordinates, but for the y coordinates, I notice that every coordinate is quadrupled. So it must be an exponential function. But I need to find out if it's a exponential decay function or exponential growth function. Okay, so we have to find out here. Let's see. Y equals a times b to the x power. And I'm going to use this point to find out what a is. So I'm going to substitute 8 in for y and 0 for x. So b to the 0 is 1, so a is 8. I'm going to write this function again with a as 8. Okay, and then my b will be 4 because 4 is the growth factor. between the y coordinates. So 4 to the x power. So as you can see, because the base here, b, is greater than 0, we can say this is an exponential growth function. Okay, part B, graph the function, identify the domain and range. Okay, you're going to find 2 points. 1 over 15 to the 0 power. Why do I use 0? Because it's the easiest. And I'm going to use -1. Why did I use -1? If I use -1, then I can just flip 1 over 15. And remember, this is the power property, a over b to the -1 power. I take the reciprocal of a over b, the power becomes 1, or +1. Okay, so I'm using the same concept. And 0, 1, it's about here. And then -1, 15, approximately. And then I'm going to try to graph this to the best of my ability. Okay, something like that. Okay, and the domain will be all real numbers, and the range will be all positive real numbers. Or you can just write y greater than 0. And for this one, I'm going to still use 0. 1/4 to the 0 power is 1, and 1 times -1 is -1. And then I'm going to use -1. So let's see. 1/4 to the -1st power. I can take the reciprocal of 1/4. Then this power becomes positive. So this will be -4. So 0, -1. And then -1, -4. Okay. In your domain, be again all real numbers. Range y less than 0, because we want all the negative numbers or coordinates below 0. Okay, and this one, plot 2 points, 0, 4, -1, 36. Okay, so 0, 4, about here, and 36, -1, 36. This is 36. The domain, all real numbers. Range, all positive real numbers, or y greater than 0. For this graph, again, I'm going to find 2 points, and we have 0, 4, and 1, 1. Okay, and again, the domain, all real numbers, range, all positive real numbers. Part C, graph the function. Compare the graph with the graph of y equals 1/5 to the x power. So first I'm going to graph this function on this graph. So x, y, and 0, 1, and I'm going to use 1, so this would be 1/5. Okay, and 1/5 is about 0.2. Okay, so 0, 1, about, and 1, 0.2. And maybe I should use one more point, -1. And if it's -1, then y should be 5. And can go ahead and plot this. Let me label this graph here. Okay, I'm going to graph this exponential function now. X, y, and I'm going to use 2 points. I think that would do. 0, 10. 1, 2. It's about here. And now I'm going to connect the coordinate points. Okay, as you can see, this graph is a vertical stretch of y equals 1/5 to the x power. It also shifted upwards to 0, 10. And thirdly, we can say the domain is all real numbers, and the range is y greater than 0. And for this third point, I'm referring to the graph in red, or in other words, the given function that we're supposed to graph. Okay? For this next exponential decay function, I'm also going to graph y equals 1/5 to the x power so we can see how the graph changes. Okay, so I'm going to plot -1, 5 again. And 1 and 1/5 right here, and 0, 1. So this is the graph that we want to compare to, this part. Okay, and then let's make a t-chart. I want to use 0. 1/5 to the 0 power is 1 times -5 is -5. I'm going to use 1. 1/5 to the first power is still 1/5 times -5 gives you -1. So 0, -5. I'm going to label my points. 1, -1. Okay, let's see what happened to the graph here. First of all, it's a vertical stretch. Of y equals 1/5 to the x power. Secondly, is shifted down to 0, -5. Thirdly, it's also a reflection in the x-axis. And I'm going to write the domain, all real numbers. And range would be all negative numbers below 0. So as you can see, this graph here has stretched a little bit compared to the graph y equals 1/5 to the x power. Okay, so if we draw the imaginary line here, you can see that it's not exactly a reflection. The graph has been stretched. Alright? Okay, for this exponential function, I'm going to again graph the graph we're going to compare it to. So y equals 1/5 to the x power. Okay, so again I'm going to use the point 0, 1, and 1 and 1/5. Okay, so this is the original graph we would like to compare it to. Okay, and let's find 2 points for this given exponential function. It's 0, then that'll be -1/5, and then -1. If we use -1, we flip 1 over 5, and that will be 5 times -1/5. That will be -1. So 0, -1/5 is about here. -1, -1. Okay, we can go ahead and connect. So as we can see, this red graph is a vertical shrink of y equals 1/5 to the x power. As we draw an imaginary line, we'll notice that it's not an exact reflection. It actually shrunk towards the left direction. And then we can also say it shifted down to 0, -1/5. And we can also say it's a reflection in the x-axis. And fourthly, domain, all real numbers, range y less than 0. Okay, everything below 0 along the y-axis. And we'll continue the second half of this lesson in the next video.